let's start talking about recursion and to to maybe revisit the issue or revisit the idea. Let's go back to when we did this in C. Okay, and the example that we did when we did it in C was to compute the factorial. Okay, we'll just run with that exact same example here um, for doing this in assembly, and then guess, of course, what your assignment will be. If we do the factorials, you guys will be doing the Fibonacci's or something. Okay, so yeah, big shock. Okay, and so the view of the Fibonacci's, or sorry, not Fibonacci's, of the factorial function that we did was, well, what is in factorial? You compute recursively the factorial of one less than that, get that answer, and then multiply it by n, right? So it recursively sort of multiplies down the chain. And then what's our base case here? What's 0 factorial or 1 factorial? One, okay. And obviously it couldn't be 0 because if we're multiplying, then we'd get 0, and that's not a good thing, right? Yeah, so the base case, we just defined that 1 factorial is 1. That makes sense. And then we could also define 0 factorial being 1. Okay, good. So the base case is just in the if statement here, right? If the input value is 1 or smaller, then just the answer is 1. Okay, no big deal. Otherwise, you take that number and multiply it by the calling factorial with 1 smaller, and then you get your thing, you return the answer, and because this function fact is calling itself, that's what makes it recursive. Yeah? Okay. Good. So, and then when we did this, we had our main routine that handled the getting the input value from the user, and then also calling the factorial function, and then handling the printing and stuff. Okay, so we'll structure things very much the same way today, where we'll have a main function that does input, gets a number from the user, prints an answer back to the user, and calls the factorial function. And then we'll have a separate function that does the actual factorial part. And we have to do it that way for reasons that'll become clear as we kind of get into this. And where is everybody today? Even Patrick's missing. Um, Maybe we should. Also, I do have a question. Have some of you guys watched a recording video from, say, within the last week? Okay. Is it doing like a flickering thing? Okay, because it's doing this flickering thing on my uh, preview window here, and it wasn't clear to me if that was um, yeah, it is doing the flickering thing there, Patrick. I don't know why it's doing that. So I'll try and figure it out. But yeah, I know it's annoying. I'm not sure why it's doing it. Because yeah, it does look kind of annoying. Um, and okay, so there must be something. Let me try that. Okay, let's see if maybe this is better. No, it's not the terminal window, Patrick, because it's doing it over the entire bottom half of the screen. There's something wrong with the input. And I'm trying to change some presets here to maybe make it go better. Yeah, okay. I don't know what the issue is. I'll try and figure it out because it's getting worse, and this is getting really annoying. Okay, well, anyway, we'll continue with it. Um, At least the top half is somewhat readable. So okay, so let's do here. Let's basically define a new program, okay, and we want let's do recursion. Well, let me just call it factorial since I've already used the recursion for the C version. Okay, and let me actually keep the C version open just for reference. Okay, so a couple things we need to do. The first is we should probably, well, let's get the shell in. And switch the syntax highlighting. And then get the usual suspects in. Okay. We also need to have our factorial function, which I'll put down here. Okay, and we'll make it also a global. And for reasons that'll become clear, let's also do the same thing with this stack pointer. Here. Okay, so yeah, there. Okay, and then okay, we're good. All right, so we need to accept an input number from the user. So we should prompt the user, right? And then also have an output string that we could, so we need some strings and stuff to do the printing. Okay, so let's just do string one will be ASCII, please input a number. String two will be factorial of percent. We'll go ahead and do li here instead of I, because, well, it doesn't really matter, right? 32-bit, 64-bit, whatever. But the factorial function grows really, really quickly, right? And so it is possible that we could put in a number and overflow a 32-bit integer without too much trouble, okay? So so we'll go ahead and do 64-bit. Okay, so we've got our output string, and then if we're going to get input from the user, then we need to tell scanf what kind of data we're pulling in, and in this case, we'll just pull in a 64-bit integer, okay, so a long integer. Okay, and we will not need in this particular instance, in this particular program, we will not need the flush function because, or at least not right now. Okay, when did we need the flush function when we were doing scanf stuff in C or getcar, one of the two? We only actually needed it if we ever did two instances of user input, not one, okay? Because the first input of user instance, we needed to clear the input buffer afterwards so that the second input didn't get screwed up, okay? So, for example, where you guys did that was with the Caesarean cipher thing. You took in a string and then you prompted the user for a number for the shift amount, right? And you guys saw that if you didn't have the flush function in between, then the number input was all screwed up. It didn't work correctly. Okay, so we would have to do that if we were doing multiple inputs, or if let's say, for example, I wanted to put in some error checking here and say, if the user gives me a bad input that's not actually a valid number, then reprompt them for the input. Okay, we'll look at how you could do something like that later. Okay, but for now, we'll just assume the user isn't a complete moron and does what they're supposed to do. Okay, so the other thing we should probably do is we know that we're going to get a long integer in from the user. Okay, and similarly, we know that we're going to have a long integer for our answer, right? And so at the end, we need to print two long integers. Okay. Now we've got a couple of options here. If I use scanf to get data from the user, okay, I have to put that data in memory someplace. Yes? So where in memory should it go? Well, that's kind of a touchy subject, right? There are lots of different places we could put it. We could handle it sort of dynamically, or we could pre-allocate space for that right now, okay? And just for sake of demonstration, let me go ahead and pre-allocate the space for the input number that the user gives us and the final answer that we'll end up printing, okay? And as you'll see, we'll have to dynamically worry about a few other things, but we'll get there. Okay, so let's call it num1, and let's do this. Okay, so let's make num1 the value that the user inputs and num2 the answer. Okay, and I'm just going to go ahead and initialize them to 0 and 1 respectively. But obviously, when we prompt the user for input and we type something, that will change num1. And then when the function does its computation, that'll change num2. Okay, but we're just pre-allocating some space in memory to store both of those values. Seem reasonable? Yeah? Okay. So let's get the input handling working. Okay, so what do I need to do to call printf for the to prompt the user? Well, I need to load x0 with what? The address of the string. Okay, and here string 1 is the thing that says please type a number. Okay, and then I can just branch to puts or printf. I'll use puts here because we don't have any formatting to deal with. Okay, fine. And then what? Well, I need to actually get the data from the user. Okay, so I need to call scanf. All right, what information do I need to give scanf in order for it to function correctly? Yeah, I need to give it the location of where it's supposed to put the data that it gets in, and the same thing, right? Where am I going to put the data? But also, what's the format string that describes what kind of data I'm getting, right? Okay, so the string 2 is my, or sorry, not, is it string 2 or string 3? String 3. String 3 is the format string that tells me what kind of data scanf should get. Okay, in this case, a 64-bit integer. Okay, and where is that number going to go? It's going to go to wherever num1 is stored in memory. Okay, so what do I have to put in register x0 to call scanf? What has to go in x0? String 3's address, right? The pointer to it. Yes? Okay, so string 3's address, and actually, Patrick, I just had an idea that might explain why we're getting this flickering. 60 hertz. I think I fixed it. Nope, damn it. Shit. Well, maybe it seems a little better. No, now it seems almost worse. Okay. Patrick, I really don't know what's going on with that. I'll have to mess around. Okay, anyway, where was I? So what do I have to put in register X0? The address of the format string. What do I have to put in register X1? The address where I'm going to write the data. Okay, so for scanf and printf, the format string always, its pointer goes in X0, always, period, end of statement. And for scanf, I really need to tell it two things: what kind of data it's getting and where to put it. Okay, and in this case, I'm choosing to put it. This is why I pre-allocated the number num1. So I have wherever that place is in memory. The scanf is going to write that. Okay, so we're good there. And then so that'll get us our data. And then let's just go ahead and print the two values. So if I want to do this, then looking back at my print thing, I need to give printf three values. X0 is going to have the address of string 2. X1 is going to have the first number, the input number, and X2 is going to have the second number, right? Okay, so right now, well, LDR X0, this would be string 2. All right, that one's easy. I need X1 to have my input number, but where is the input number out in memory? I don't know, right? So if I do this, that will get me the pointer to X1. Okay, but what do I really want here to be in X1? The actual number itself. Okay, so I'll do this. I'll put the address in X3 and then load and do this indirect load to get it into X1. Okay, and I'll do the same thing for the other number. I'll load X3 with its address, and I'll load X2 with that indirectly. Okay, so what will be in X3 here when I get to the printf? The address of the second number, but am I going to be printing that? No, so I don't really care. It's just there. Okay. Okay, so this is the memory indirection that we've done before. And right. So right now, all it's going to do is the Fibonacci of 0 is 1, okay, is what it'll tell us. Or not Fibonacci, a factorial, okay? It'll tell us the factorial of 0 is 1. And the only reason it'll do that is because did I ever actually change num0 or the two numbers? Right now, no. I just initialized them to be 0 and 1 respectively, and I haven't even written the factorial function yet. Okay, all I'm doing is getting the printing stuff working, and let's double check that that all is correct. All right, so we want to go to recursion, and it was factorial, so let's do as factorial, and I'll go ahead and do it with the debugging flags, just so we've got that. Okay, so the input handling works, and it's going to say the factorial of, well, whatever number I typed is 1. Okay, and it's going to always say that the answer is 1 because I haven't actually written the function to compute the factorial yet. Right? We'll obviously get there. Okay, so questions so far? We Gucci? We? No. Okay, so got that. Okay, so now the factorial part. Okay, this is where it's going to get fun. Okay, so before we talk about that, okay, um, or the actual details, let me kind of sketch out an idea here on my iPad just to give us a sense for one of the things that we're going to have to do. Okay, so with memory, okay, your memory segment, your program really kind of gets like 4 segments worth of stuff. Okay, there's a data section, right, which we've seen. Okay, and this is non-executable. And it's sort of pre-allocated. Okay, the text section is really where the program is. This is executable. It's also pre-allocated by the operating system. Right, the operating system puts your program in memory someplace. Okay, it's also read-only, generally. Okay, now this is sort of an interesting thing. You want your program code, generally speaking, to be read-only as sort of a security measure, right? Um, and but you can do something kind of cool if you allow it to be writable, which is to say you can have a self-modifying program. Okay, and I've written one of those. Well, okay, so you guys, those of you who took 101, you remember when we did the Brookshire assembly machine, right? And we talked about multiplication, for example. Um, there is a method of doing multiplication called quarter square multiplication. And to implement that on the Brookshire machine, you actually have to do a self-modifying program, which is kind of interesting, right? Um, for our purposes, though, we probably will never actually have to do a self-modifying program. Okay. All right, so you've got those 2 sections. And then you have 2 other piles of data, okay, that are called the heap and the stack, okay? And we're going to really concentrate today on the stack. So the stack, well, okay, how many of you guys have taken CS211 at this point? Okay, good, some of you. All right, so what is a stack? Yeah. Okay, so that's a pretty good description, right? It's sort of a linear data structure. Um, in this case, it's just a pile of memory. But how you put things on and off the stack, there are rules about that, and there are a couple of varieties of rules about that. Okay. Um, so a, a stack, in some sense, you can almost imagine as being like um, so you guys, those of you who are in fraternities probably have these, but do you have one of those like things where you store plates and it's like a giant spring-loaded thing and you put plates in and you push them down and they go down into this like cavity or whatever? You kind of know what I'm talking about? Or maybe you've seen these in a cafeteria. Okay. So in some sense, you can think of a stack as kind of like being that, right? You can push something onto the stack, and when you push something onto the stack, you're putting it on one end, okay, and always that one end. And when you pop something off of the stack, well, you can only take off the top plate. You can't like magically reach in and grab the 5th plate down because it's inside that cylinder, okay? So, in some sense, and this isn't a perfect analogy, but in some sense, you can sort of think of the stack like that, okay? Now, on most of these architectures, and ARM included, the stack it grows downwards, okay? So if I have some big pile of memory here, okay, I'm going to think of this as being some segment of RAM, okay? The stack starts here at some initial value, okay? And there's a pointer that always points to the bottom of the stack. and this is called the stack pointer. Okay, so this SP, every time we've stored X29 and X30, right, the SP that I've written there actually stands for stack pointer. Okay, and um, so if I want to put data onto the stack, then I need to specify that I want to put data onto the stack, but I also need to do something with the stack pointer, okay? So the stack pointer should always point to the bottom of the stack, okay? So in our plates analogy, it doesn't really fit, but it's almost like as if the plate thing is on the ceiling, okay? It's not really the best example here, but yeah, okay. So the thing that's maybe a little bit confusing initially is that the stack grows downwards, not upwards. Okay, meaning, so what do I mean by down? Well, the initial stack pointer is some memory address. As the stack grows, the stack pointer's value is a smaller memory address. We start at higher memory addresses and we expand into lower memory addresses. Okay, is that all right? Now the heap works the other way. It grows from the bottom and comes up. Um, and we'll talk about that later, but yeah. Okay, so the thing about the stack pointer that we have to be careful with is that it changes as the program executes. Okay, the other thing that we have to be careful about is that we need to restore, the stack pointer should start at something and end at that exact same thing. Okay, and if it doesn't, that's going to be another way that you guys can end up with seg faults, okay, because of what we will need to store onto the stack. Okay, so the initial stack pointer before your program does anything is some value, okay, and it's usually 7F, blah, 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 okay. That's just the operating system virtual memory just does that, okay. So it's some number, right? And then as you grow your stack, that means that your stack pointer is going to start getting us to be a smaller number because it's pointing to a smaller memory address. Okay, and then when your program concludes, the stack had better be back the way it started. Okay, and if it isn't, then you probably will get a seg fault. Okay, now the other thing, and this is specific to the ARM architecture, is the stack pointer always must be always must be a multiple of 16. Okay, so in hex, its final hex digit is always a 0. Okay, if you do not have a stack pointer that's a multiple of 16, then what you will get is called a bus error. Okay, and you'll see this. It's slightly different than a seg fault, um, but yeah, you will get that error. Okay, so stack pointer must be a multiple of 16. Period, period, end of statement, don't argue. Okay, all right, so let's go back to the the pi. Okay, so when we start our program and end it, we always had these instructions, this STP thing, and then there was an LDP at the bottom. Okay, what that's going to do is it's going to take the values of X29 and X30, it's going to store them onto the stack. Okay, now this bit here is a little bit confusing. Okay, because what it's going to do is um, it's going to say, okay, the stack pointer is here. I want you to put the data below the stack pointer, okay, at these two values. And then when it's complete, I want you to take 16 away from the stack pointer, okay? So now the stack pointer is at the bottom and these two things are right on top of it, okay? Okay, then on the other end, when we load, we're pulling the plates off the stack, okay? Where are they relative to the stack pointer? Well, they're wherever the stack pointer is. And after that operation of pulling the data off is complete, I want to raise the stack pointer back to its sort of starting value, Okay. All right. So let's look at this in GDB to kind of see it in action. Okay. And it'll be a little more clear, hopefully, there. Okay. Um, okay, let's not worry about that error. I probably just saved something. Okay, so what I want to look at, and I have not executed a single line of code yet. The instruction I'm about to execute is this STP thing, okay? So let's look at the registers, okay? What is the starting value of the stack pointer for the program does anything, okay? It's here. The stack pointer is a special register within the processor, okay? And in our case, it's in some sense X31, okay? But we'll always just refer to it by the name SP, okay? And what is it? Well, like I said, it starts out as 7FFFF something or other, okay? In this case, we got blah, 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 EF90, okay, is our stack pointer. That's the starting value, okay? All right, and I need to push onto the stack two values, x29 and x30, okay? And these have to do with the breadcrumb thing, right, to get our way back out of the forest in the Hansel and Gretel story, okay? So the data that I want to push onto the stack is the value of x29 and the value of x30. Now, the value of x29 has another special meaning, which I'll talk about later, but notice how it actually starts as the same number as the stack pointer, okay? Which is not coincidence, okay? And then X30, this 400 AAC, okay, that's down in our either our data or text section, okay? So those two values, okay, I need to push onto the stack, okay, and the X20 or sorry the X30 value, this 400 AAC, is basically the address where when we hit the return instruction, um, we need to the return instruction for our program basically needs to return to the operating system, and that memory address 400 AAC has the instructions for how the program should do that. Okay, so the operating system deals with that part. Okay, okay. So right now our stack pointer is, what did I say it was? 7FFFFEF90. Okay, so if I look in memory, um, starting at the stack pointer, and actually what I want to do is, let me do 7FFFFF well, let me do, say, 80, okay? So I'm a little bit shy of the actual stack, right? The stack pointer is currently pointing to here, okay? And it's going to decrease after this instruction to actually point to the memory address that's listed above. Okay, now this is maybe one thing that's annoying about GDB or the way we're thinking of a stack. What order does it list the memory addresses in? Increasing, well, yeah, I know the blue is really kind of hard to see here. I really need to figure out a way to change that. So, but anyway, so EF80 is here, EF90, A0, B0, and so on. So which way do we list memory? Do we list the lowest address at the top or the lowest address at the bottom? Well, in my sketch on the iPad, I kind of thought of the lowest address being at the bottom. Here, it's ordering them at the lowest address at the top. Is that annoying? Okay, just get over it, right? Like, there's only, the world's not perfect. Okay, so, right. So, Okay, so what happens to be at the memory addresses that are right above this here? Okay, so at EF80. Well, 400280, some zeros. Okay, but doesn't look like it's anything in particularly special at this moment. Okay, well, so let's execute the actual instruction that's going to do this store pair thing. Okay, and so what I want to keep track of is what's the current value of the stack pointer before I execute this instruction. EF90. Okay, so scribble that down someplace for me. Okay, and what is in memory? Well, at EF80 and 90, nothing special. Yes? Okay, so if I step, what is the stack pointer now? EF80, so it's gone down by 16 bytes. Okay, and if I look at in memory, what is at EF80 and EF88? At EF80, what is this? Okay, so the value there, right, the way you read this is it's 7F, EF90. Okay, where did that number come from? It was X29's value, right? So I've put X29's value in memory. It's a 64-bit number, so it takes up 8 bytes. There they are. Okay, but I also put X30 into memory, yes? Okay, and where did he end up? Well, there, 400 AAC, and then a crap load more zeros, right? Because it's a small number. And what is the stack pointer's value now? It's not blah, blah, blah 90, but rather EF80. Okay, so I have expanded the stack by 16 bytes and put 16 bytes worth of data onto it. Okay? All right, now, what these values are, okay, the value of X29 is called the frame pointer, and like I said, we'll talk about what that means later. We could get away without worrying about it because our program frame pointer never changes, but we'll just leave it just in case. Okay, and then X30 is called the link register. Okay, the link register is critical for how you handle the branching and linking. Okay, it's part of the breadcrumb system. Okay, so the program counter, okay, which is listed there, PC, program counter, and in some architectures, it's actually called the instruction pointer, which is in some sense a better name for it, okay? Because, well, what does a pointer do? What is a pointer of any kind? Yeah, it's the address of something, right? It points in memory to something. And instruction pointer, I think, like I said, is maybe a better name for it because it's pointing in memory where is the next instruction that you're about to load and execute. Okay, so as a program runs, this instruction pointer counts up, right? It starts at some value and it counts up to move down the line to the next instruction, and so on. Okay, and when we do branching, what we're doing is rewriting the value of that. We're changing that pointer, okay, and saying, oh, I actually want you to go way over there and start executing code. So I change the value of the program counter to that thing. Okay, so when I do a branch and a link, that's what I'm doing. Well, or branch, but when I do a branch instruction, what I'm doing is changing the value of the program counter to say, oh, I want you to start executing code over here. Okay, and on this architecture and in all of the manuals that ARM describes, they call this the program counter. On Intel, I think they usually call it the instruction pointer, but they mean the same thing. So if you see instruction pointer out in the wild, that's what you're looking at, program counter. Okay, okay. So the link register here, okay, like I said, is 400 AAC, okay? And if we look at what is in memory there, I'll just start at AA0, okay? Um, what's there is basically stuff for the operating system for how to basically get back, how to exit the program. So that's sort of the you know, how do you get right out of the forest? You're at the edge of the forest. Now what? Okay. All right. So let's see, where were we? Well, okay. Yes. Okay. So let me do this. So we're about to print. I'm about to execute this BL puts instruction. Okay, which is going to just put the string on the screen that says, "Hey, please type something." Okay, great. Yes. Okay. So what I'd like to look at for right this instant is what is in X30 right now. 400 AAC. Okay. I'm about to execute this puts instruction. Okay. What's in X30 now? Okay. Now, what's special about 0007 or 400734? Let's look in memory. And I'll look at 730 to start. Okay. 730. So 734 would be here. It'd be this 32-bit number. Okay. All right. Does that 32-bit number look like anything in particularly special? I don't know what that corresponds to. Okay. Well, actually, I do, but it's an instruction. Okay. That's actually code. Okay. So we're looking at our program's code in that part of memory. Okay. So when I call a function, right, that function needs to know where does it go back to when it finishes running. And in our case, where does it go back to? It goes to the instruction immediately after puts, okay, which happens to be at that memory address, okay. Um, okay, so that's how puts knows where to go back to and continue executing instructions, okay. All right, now we still haven't done a dang thing with the factorials, and so let's get to that. Okay, so what does my factorial function need to do? Well, first thing, let's get the base case dealt with, okay? And second thing, let's remember our calling convention. How many variables or values does factorial take in? Just one, okay? How many values does it return? Also just one, right? You put in a number, it spits out a new number. Okay, so according to the calling convention, you guys might think I'm a broken record at this point, and I'm sorry. What is the calling convention? Where must we pass the number to the factorial function? In register what? 0, okay? And in our case, it'll be x0 because we're doing a 64-bit stuff, not 32-bit, okay? And the number that I return from the function should also be where? X0. Okay, so got to have that. And so when I call this function, okay, in order for me to call the function, what I need to do, okay, so I called it fact. I need to branch and link to it, but I also need to make sure that x0 has the correct value in it. And what's the number that I want to pass to this function? It's num1, right? So let me load x1 with the address of that, and then I'll put that actual number in x0. Okay, so now whatever number I typed and put out in memory, I pulled it back out of memory, put it in x0, and I'm giving it to the factorial function. Okay, good? No. And then the factorial function is going to do something. And right this instant, what's it going to do? Well, nothing, right? There's no code yet. Okay, so it would in this case just return exactly what came in because I haven't done anything yet. Okay. Okay. Mm-hmm. Oh, so I had to I needed to load the address of the number in memory so that I could actually load it into a register. And I need to load the number that I want to pass to the function into x0 to obey the calling convention. So the memory address, what register should I load him into? It doesn't matter, but it can't be x0. The value is going to go in x0. The memory address needs to go someplace else. Okay, so I just put the memory address in x1 and then went out to that memory address, pulled whatever's there, put it in x0, and that's our number that the user typed, okay, whatever value it is. Okay, and then I'm going to pass that to the factorial function, and the factorial function will say, oh, look, there's something in x0. This is what I'm supposed to work with, and then it'll do its thing. Okay, good? Okay, so let's get the base case working first. Okay, and what I'm going to do here is I'm going to put in a label, and I'll call this fact base to mean the base case. And then I'll also have fact recurse. Okay, and then I'll also have here my end instruction, which will be that piece. Okay, just to kind of section off the pieces that we're looking at. Okay, so what's the base case need to do? Well, we get a value in, well, so actually before we do that, let's come up here. How do I decide whether or not I'm going to do the base case or the recursive case? I need to do a comparison and see if my number is 0 or 1, or let's just say less than 1, or less than or equal to. Okay, so I'll compare x0 with the number 1. Okay, so I can compare register to register, or I can compare register to immediate. Okay, and in this case, we'll just do 1. Okay, and then I need to branch on what condition to where. Yeah, okay, so if it's less than or equal to, I'll go to my base case. So let me save myself some trouble and do greater than to the recursive case. And then I'd only have to have one branch instruction. Okay, because if I don't jump to fact recurse, then I'll just continue right into fact base. Okay, good. All right, what's the answer to the factorial function if I do put in a number that's 1 or smaller? 1. Okay, I need to return this number. Where does that number need to go to be returned correctly? x0, calling convention. So I just want to move x0 to have the number 1 in it. And is there anything else I need to do besides return? Nope. And so here I can branch to end. And that will skip me over the recursive case. I'll do the breadcrumb thing and return, and that's it. Okay, so the recursive case is, the base case is easy. Okay, good. Okay, so the recursive case. This is where it's going to get fun. What was the recursive case in C? What did I need to do? The value I'm going to return is n times the factorial of n minus 1. Yes? Okay. So I need to have two numbers at my disposal, the current value of n and the answer to factorial of n minus 1. Okay? All right, so here's where it's going to get fun. Where is the value of n that's coming into the recursive case? It's sitting where? In x0. Yes? I need to stash that number for later use. Okay? Because I also need to take one away from it and hand that to the function again. So if I want to stash what's currently in x0 into a safe place, where would be a good safe place to do it? Okay, so I could stash it into a register, right? And previously we've used x19 and on up through what, 27, 28, as safe spaces where we can stash values. But what I want to convince you is that I can't do that here. Okay, and here's why. Let's suppose that I wanted to compute 10 factorial. Then through the course of going through all this, I would need to stash the numbers 10, 9, 8, 7, 6, 5, 4, 3, 2, and, well, that's it, right? 9 numbers. But what about if I'm a jerk and I want to compute 30 factorial? How many numbers do I need to stash? A lot. More than I have registers. Okay, so conclusion, registers cannot be our stash safe spot. Okay, because we don't know how many of them we're going to need. For a given running of this program, we could need 5 or we could need 500. I have no idea. Okay, and since I don't know in advance, I can't use the registers as that thing. But what I can use is memory, because how much memory do I have to work with? Oodles, right? I got as much memory essentially as I could possibly want. Now, it's a finite number, yes, but I'm not going to run out of memory. I will run out of registers. Okay? Okay, so what I need to do is I need to push the value of n onto the stack. Because if I can't put it in a register, I got to put it into memory. Okay, so what I'm going to do is I'm going to put what's currently in x0 onto the stack. And I'm going to do this with the instruction store register, STR. Okay, so you remember the STP that we had at the very beginning of our program? What did the P stand for? Pair. Okay, it stored 2 registers to memory at once. But if I only want to do one of them, then I'll do this. Okay, and which register do I need to stash? I need to stash X0. Okay. And I need to stash it someplace on the stack, and so we'll actually use the same kind of syntax that we did a minute ago, okay, which is where is it going? Basically 16 under the stack pointer, change the stack pointer, okay? So think of this as what's called a push x0 onto, it's a push operation. I'm pushing a plate into my magic plate plunger thing, okay? Okay, and then, so what do I need to pass factorial in the recursive case? I need to compute the factorial of 1 smaller, right? So if I'm doing 5 factorial, I have the number 5 and I need to compute 4 factorial, yes? Okay, so where is the number currently that I need to compute the factorial of? It's sitting in x0. What do I need to do to that? I need to take 1 away, right? So let me just subtract 1 from x0. Okay, so that's n minus 1. And that number I'm leaving in x0 because according to the calling convention, where do I pass that value to factorial? In x0. Yes? Okay. So here is where I'll branch and link to fact. Okay. So these two lines here, this is compute n minus 1, and then this one is compute n minus 1 factorial. I don't know why the syntax highlighting didn't make that one green. Yeah, whatever. Okay, so I'm passing n minus 1, okay, to my function, okay, and it's going to do its thing, okay. Let's just pretend for the moment that it magically returns the correct value. Okay, so let's say that I'm, for example, computing 5 times 4 factorial. It magically is computed that 4 factorial is what? 24, right? Okay, so let's just say that, right? So my value 5 is on the stack. My value 24 is in which register is it going to be when I come back from the fact function? X0, calling convention. Okay, so X0 has the number 24, and the number 5 is sitting out in memory. And I need to take those two numbers and multiply them. Yes? Okay, so I need to pull the number 5 off of the stack. Okay, and so how should I do that? Well, let me load it, load register, and okay, which register do I want to put that number into? Should I put it into register 0? No, I should put it into someplace else. Let's do register 1. And okay, so this is pop in off the stack into X1. Okay, so what's sitting in X0 right now? The answer to factorial. Okay, so let's say that's 24. What's sitting in X1? The number 5. What do I need to do with those two numbers? Multiply them. And where should I put that answer to obey the calling convention? X0. Okay, that's where the return value, so this is the annoying part, right? It's both the input and the output value needs to be in X0. So who's in X0 at any given time is, of course, changing. Okay, all right, so I need to multiply them. Well, how do I multiply numbers? We've never actually used that instruction yet, but how did I add numbers? If I wanted to add two registers, I had to specify three things: destination and the two sources, right? And what was the add instruction? Add. Well, guess what? What do you think the multiply instruction is? Mul. Okay, so just mul. And like with add, there are different versions that set flags and blah, 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 but we'll just use straight mul here. Okay, so x0 is the destination, and I want to multiply x0 and x1 together. Okay, so if the factorial function had magically returned 24, and I had 5 in x0, I'd do 5 times 24, I'd get 120. Good, that's my return value, and I'm ready to end, and that's the end of it. Okay? All right, is that okay? All right, so first off, let's assemble it and make sure that I haven't screwed something up, which is, of course, always entirely possible. Up, what did I do? Oh, okay. It doesn't like me to use dashes. Okay, so we'll call it fact base and fact recurse. Is that okay? Just without the dashes. Okay, good. Okay, I think you guys would agree that that's not correct. Oh, no, 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 I know why. Sorry. Because we computed it, but we never actually put it back into memory. So what's in X0, I need to store that to memory. So I need to load X1 with the address of num2 and then store X0 where X1 is. So basically we computed it, but then we never stashed it into memory for later use. Okay, so let's try that again. There we go. Okay, so the factorial function was fine. It was just I threw away the number. Okay, okay. All right, now let's go down the rabbit hole. So the rabbit hole is, let's go through this in GDB. Okay, so I'm going to start executing instructions. We'll start from the beginning. Okay, step, I'm going to load in some stuff. Please input a number, do a thing, get a number. I'll type in 5. I'm going to load the address of okay, so I just typed in the number 5, okay, and I scanf put it out of memory, and I just pulled it out of memory to put it in register 0. All right, so what's in register X0 right now? 5, okay, and I'm about to branch to the factorial function. Okay, so I just stepped and jumped to the factorial part of the function, which is going to store its own stack stuff. It's going to compare, okay, and in this case, is 5 greater than 1? Definitely. So I'm going to go to fact recurse case, and here I am. So what's it going to do? It's going to push X0 onto the stack. Where is our stack pointer? It's blah, 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 80. So let me look at starting at EF70 just for giggles. Okay. What do I see here currently? I haven't done anything to the stack yet. I haven't pushed anything to the stack yet. Okay, there's some values there, whatever. Have I put the number 5 onto the stack yet? No. I'm about to. Okay, so let's do that. Okay, so 2 things have happened. What's the stack pointer now? Not 70, but 60. And if I look in memory at that address, 60, what do I see? The number 5. Okay, that's good. Okay, now here's where you got to buckle your seatbelts. Okay, so I just stashed, and I'm going to compute, take 1 away. So what's in register X0? Four. Why 4? I subtracted 1 from 5. Okay, and I'm about to hand the number 4 to my fact function, which takes me back to factorial, and the stack is going to grow. Okay, so what's my stack pointer now? It's shrunk. Now I've stashed this stuff, okay, which are the breadcrumbs, right? So what you should see when you look at this is breadcrumb, stashed number, breadcrumb. And as I continue this, just bear with me for a moment. And actually, let me expand it to a little bit bigger. Okay, so we're looking at a whole big old pile of memory here, I reckon. And what do I see? 5 breadcrumbs, 4 breadcrumbs, 3 breadcrumbs, 2 breadcrumbs. And do I ever have to push 1 onto the stack? No, because what's factorial of 1? 1, so I don't have to worry about that, okay? And so now I'm about to return the number 1, and the stack is going to grow back up as I kind of pop my way out of the recursion. And so I'll have 1 times 2, then that times 3, then that times 4, and that times 5, and then I'll follow my breadcrumbs back and terminate. Okay? All right, so let's keep going here. And oh, sorry, I need to step. Okay. Then I'm returning, popping, multiplying, 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 exiting, pop it, multiplying, exiting, pop it, and then I'm done. I'm back out of the factorial function. And where is my stack pointer? Has been returned to 80, which is what it was before I went into this factorial rabbit hole. Okay. Now that data that I've written is all still out there in memory, right? I never deleted it, but I have changed the stack pointer, okay, which is to say sort of which plate is on top of the thing, right? Okay, so if I look at memory starting at 7 FFFFF say 00, okay, then what can I see? Do I still see my breadcrumb trail and my numbers that I've stored? Yeah, they're all still there. It's just that the stack pointer is now pointing to address 80, which is the final breadcrumbs for my program to quit. Okay. All right. So let's step through the final stuff and make sure, see it working. Step, load the number, load the number, load the other number, load the string, branch to printf, and it prints the factorial of 5 is 120. Move W0, return to the operating system, and it's done. Okay, that was fun, wasn't it? Not really. Okay, was that kind of confusing? Very. Okay, and I get that, right? This will take a little bit of time to sink in. And so one of the things that I've been working on kind of in my, copious spare time, you guys know how much free time I have, is, well, how many of you guys have watched videos on YouTube either by, well, I showed a computer file video to my 101 class yesterday. Has anybody watched anything on number file or computer file? Yeah. Okay. Or really, lots of other really good, like educational YouTube content. What do they have? They've got really slick animations and stuff that they're doing like in After Effects or whatever, right? Guess what Dr. McKinney is learning? Yeah, how to do animations and stuff. So how can I make a video that animates this a little bit more clearly? And that's going to take me probably hundreds of hours, okay, to get this for one lesson, right? That's the investment you have to make. So by the way, if any of you guys want to become like big YouTube sensations or whatever, do you have any idea how much work it takes to get 1 minute worth of YouTube content, like high quality YouTube content? It's probably a factor of 1 hour to 1 minute, roughly. Okay, and in my case, for what I'm imagining for a video on this uh, stack pointer recursion link register breadcrumb thing, okay, yeah, I still need to learn After Effects, which I don't yet know. I mean, I started working with it, but yeah. Okay, so yeah, this is a bit confusing, right? And this is maybe um, why I've tried to use GDB here. And what I need to do is like do that, but then like highlight or put boxes around the stuff that we care about. Um, and yeah, because this is kind of, like I said, it is kind of confusing. Um, so just to maybe talk of a hint, if you will, what's going to be the interesting issue that you're going to run into when you do factorials instead, or sorry, Fibonacci's instead of factorials? The value of Fibonacci of n is Fibonacci of n minus 1 plus Fibonacci of n minus 2. So it does addition instead of multiplication. Okay, fine, whatever. But the interesting part is that to compute the fifth Fibonacci number, what do you have to know? The fourth and the third. It's doubly recursive. Hmm, interesting. Okay. So what that means is that whereas in the factorial thing I only had one push pop, you're going to have in some way two push pops and be careful about how you do it. Okay. Um, and then it'll do its addition instead of multiplication, but whatever. Okay. Now, the good thing is, have you already written the the Fibonacci function in C? Yes. Okay. The recursive version. Okay. So you've already done it in C. And so the sort of broad stroke structure is not a huge mystery. Also, with the Fibonacci's, what's the base case? If the number you input is 1 or 2, what do you return? 1. Okay. And we're just going to go with the convention that the Fibonacci start with 1 and the n value is 1. So 1, 1, 2, 3, 5, 8, and so on. Okay. And that's not the only convention for it, but if you just say n equals 1, output equals 1, n equals 2, output equals 1, we'll all have the exact same sequence and it will keep me from ripping my hair out. Okay. Does that sound okay? Okay. All right. We should probably quit. See you guys whenever.